So I just put together one slide. I don't want to take up much of this discussion myself. But just to kick things off, let me start by reminding everybody of one of Alexei Kitaev's classic results. Now 20 years ago, he taught us that if you take spinless fermions in 1D, gap them out by Cooper pairing, out comes Majorana zero modes, which underlie all of the non-abelian anion physics that is the subject of this nice conference. So I will loosely try to unify the three beautiful talks that we heard in this session as proposing novel routes towards solving the first part of that equation, namely trying to get spinless fermions in 1D. So the canonical way of trying to lift spin degeneracy, which is I think most commonly pursued in this game, is to apply external magnetic fields and rely on Zeeman splitting. That obviously is has some tension with the second part of the equation, trying to get Cooper pairing. Usually magnetic fields and superconductivity are not the most natural friends. And so the subject of Omri Lesser's talk was to try to break time versal symmetry in a less invasive way, not using external magnetic fields at least of any appreciable magnitude, but instead exploiting phase control. The idea was you can instead use superconducting islands, and by controlling the phases of those superconducting islands in certain ways, you can provide a very appealing route towards topological superconductivity. That's not detrimental to the existence of superconductivity in the first place. So Solei's talk that we just heard from pursued a different route to eliminating the magnetic field requirement. In Solei's devices, time versal symmetry was broken using proximity effect of the ferromagnetic insulator. So these devices are quite a bit subtle, in part because, at least to my understanding, the europium sulfide is having an indirect proximity effect on the indium arsenide via aluminum, and ideally, I suppose you would like for a direct ferromagnetic proximity effect with the degrees of freedom that you care about. But despite those subtleties, if you can make a device like this, a very compact device that reproducibly gives Majorana zero modes, that could be a real game changer, especially from the perspective of long-term technologies. And finally, Philip Kim's talk used a completely different strategy to try to get spinless fermions in 1D. So Philip used the quantum Hall regime and tried to manufacture single channel wires by exploiting quantum Hall edge states. And these systems are amazing for a number of reasons. In the integer regime, you can get Majorana zero modes in yet a different fashion. But if you go to the fractional quantum Hall regime, which Philip has indeed done, then you have a chance to get Majorana generalizations called parafermions. But I would like to give even a further zoomed out point of view on that particular experimental setup. It really demonstrates, I think, conclusively for the first time that two of the I don't think it's controversial to say all-time great condensed matter discoveries, namely fractional quantum Hall and superconductivity, have now been experimentally united, and that raises all sorts of interesting possibilities, even aside from non-abelian anion physics. So in terms of the second ingredient in this equation at the top of the slide, Cooper pairing, these three talks all pursued the same basic approach to try to basically use external superconducting materials, slap them on to our spinless fermions, and try to force in Cooper pairing. And that proximity effect idea is obviously extremely powerful approach for designing novel quantum phases, but it does raise its own can of worms. The interface quality can be a source of disorder. You can have significant charge transfer from the superconductor to whatever parasitic material you're trying to soak a pairing into. Screening can hamper your ability to tune that system, and so on. So I think it's interesting to ask, and I propose this as a discussion topic. Can we also envision new routes to getting the second part of this equation, namely Cooper pairing? And just let me just share one idea along these lines that I worked on recently, just as a kind of proof of principle that we do have more freedom that we can exploit. So down on the bottom, this is a caricature of a twisted bilayer graphene-based Majorana platform that I had worked on with my collaborators listed below. So as people probably know at this point, twisted bilayer graphene is this miraculous system. extremely tunable and rich phase diagram, including superconductivity. And so in this work, we showed as a proof of principle that it's possible to exploit that tunability and richness to engineer Majorana zero modes without ever invoking external proximity effects with superconductors anyway. And possibly if the stars align just right, you might even be able to do away with the magnetic field requirement. So I have no doubt that there are other proposals of a similar spirit that are possible. Perhaps there's even ideas out there in the literature already. But I think this is it's kind of tempting to try to use some additional flexibility for how we engineer superconductivity. So the last thing I'll do is just propose a few possible questions for discussion among this group, listed on the bottom left. Certainly, I think there's nothing unique about the four platforms listed on this slide. In this conference, we've heard about many other designs, but it's not clear, I think, until we actually have a topological qubit, what's the ideal platform. I think it's interesting to ask whether there are alternative designs that break time reversal symmetry in clever ways, or maybe generate pairing in clever ways that can improve upon existing ideas. Maybe there are new materials that we should have in mind for to exploit for non-abelian anyon engineering. Could be things like quantum magnets, van der Waals systems, and on and on. In terms of Philip's talk, he already gave us a long list of appealing experiments for the future to try to really nail down the existence of Majorana zero modes and parafermionic zero modes and quantum Hall superconductor hybrids, but maybe people in this audience have other ideas. Since this is the final discussion in this conference, perhaps there's interesting things to say about optimal experiments to go beyond zero bias peaks, which has been the premier tool to date. And finally, I wonder if it's actually useful to begin circling back to where this whole non-abelian anyon physics began originally, namely in quantum Hall and the quantum Hall regime, especially in light of recent unambiguous demonstration of abelian statistics via interferometry. Maybe it's not crazy to think that intrinsic non-abelian anyon platforms are not yet out of the game. So that's my spiel. I don't want to take up any more time myself, and I very much welcome comments from the audience.
Jason, I have a question. In your proof of principle proposal, why do you need the transition metal dechalcogenide to inject some spin orbit coupling?
Yeah, exactly. So that's the one proximity effect that we exploit. In order to make this device work as we want it to, we need spin orbit coupling. So that's still a key ingredient, like in many other Majorana proposals. And so that's the sole purpose of that TMD. The good news is that Stefan Najperge's group has actually made high quality devices, TBG, twisted bilayer graphene TMD devices using tungsten diselenide. He has directly verified the soaking up of spin orbit coupling into the graphene sheets, while simultaneously maintaining all the richness of the phase diagram. So that's to my mind the least concerning aspect of that geometry.
Can I also ask a question? Oh, sorry. It's a great presentation, Jason, thanks. A quick question, maybe not so quick, relating this part of the discussion to the previous parts. So the thing is that why people don't like magnetic field, as far as I understand, is that you break time reversal symmetry, and then, as you all yesterday mentioned, you violate Anderson's theorem, and basically theoretically there is no gap. If you have disordered states are everywhere, which makes a problem, right? So in this respect, I wanted to understand, is there any conceptual difference between magnetic field and the phase, flexing the phase difference in quasi 2D geometry, which was discussed before the break, and your left, this break universal symmetry is in phase control figure. And why one would be better than another?
I think I can suggest an answer for that.
I didn't know that you were not asleep yet, so.
I didn't go to sleep. Only can answer as well, but I think the main difference is that with the phases, you kind of concentrate the magnetic field to the area between the two superconductors. The superconductor itself doesn't have any magnetic field. There are no impurities in the superconductor, or magnetic impurities in the superconductor. So you kind of concentrate everything to the area where you have just semiconductor, and this is under control. So in that sense, it's very different.
I think I disagree with completely, because I mean, after all, there's if you have a thin magnetic field in superconductor, actually is a minor concern, because if it's a thin field, basically nothing happens in superconductor. But you have induced superconductivity in a semiconductor where everything happens. And that's where these subgap states are just everywhere in the gap.
In reality, when you put, half a Tesla on aluminum in order to get these Majoranas, I think many things happen on the surface between the superconductor and the semiconductor.
But not on superconductor, because I mean there are STM measurements on superconductor that happens there.
On the surface between the superconductor and the semiconductor.
Maybe.
Yeah. So it's kind of all the effect of the phase difference is in the area that you study and you want to operate there. So this is more under control.
You pass current, right? So you pass super currents through a semiconductor narrow layer, and I don't see why this is different. Given spin-orbit interaction also, why is it so different from just having orbital effect of magnetic field? But again, maybe numerically it's better. I don't know.
The magnetic field is much larger in value, right? To create this phase difference, you put tiny magnetic fields. So you don't have stray lines that goes through the superconductor or through the surface between the superconductor and the semiconductor. They are just not there. All what you have is this phase gradient on the normal part.
The point is that you have to kill the gap. I mean, it's transition to kill the gap anyway, right? So when you go from normal to topo, I mean from trivial to topo, you kill the gap. Right. So either by phase or by magnetic field, and that's my figure of merit, So I don't see why one would be better than another from this, simple-minded consideration.
Okay, we can discuss it in another opportunity further. My understanding that 100 or whatever 100 millitesla are very different from 1 microtesla.
I mean, isn't it kind of objectively good to not suppress the superconductivity, at least on the island, within the islands? I would think that that's a pretty big advantage. I mean, I certainly agree that you're breaking time reversal symmetry in the region that you care about, and that can, you violate Anderson's theorem, you can get subgap states and so on, and maybe that's still a problem, but nevertheless, it feels more comforting to have a
I think it's maybe a wrong feeling, because I mean, in a thin shell, nothing happens. HC2 for a thin shell depends on thickness, and you can make it quite large.
You're saying that that it's the suppression of superconductivity is not an issue at all, even in the magnetic field case if you have a thin film. Is that what I? Well,
okay, so experimentalists should answer this question, but as far as I understand, basically Zeeman effect of magnetic field on aluminum is it requires 1 Tesla or something, and this transition to topological regime happens at much lower fields, right?
Hopefully.
No, but there are orbital effects that reduce superconductivity in the superconductor itself.
I say that it's not true, because I mean, if it's a thin layer, if it's a thin superconductor, nothing happens in it. HC2 scales as 1 over the thickness squared.
Well, we know experimentally that in all this Josephson coupling effect, the orbital field were extremely important in suppressing delta.
Because it enters in the Josephson junction, not in the leads.
In the leads.
I disagree with you.
But you contradict an experiment that was done in Marcus' group, that without the Josephson lead, just a slab of superconductor on top of a semiconductor. You put parallel field and superconductor.
Well, it depends on the strength of the field. I mean, of course, if you apply 1 Tesla, you feel it.
100 millitesla.
Okay.
What can I do?
So I just wanted to note that there's 3 theorists that are debating optimal devices.
Yeah, exactly. It should be
but it's good. It's a good discussion, I think.
On the call. I think, you know, I would say that their opinion matters far more than the trio of theorists.
No, we should stop it, I mean, for sure.
Any experimentalists want to weigh in?
Maybe I can. I'm a postdoc from Charles Group. I can maybe clarify that the removal of superconductivity we saw from the incoming fields on the big slabs that Yuval was talking about, that was the induced gap. Our aluminum was still superconducting, but we just saw that our gap was reduced to 0 at 100 millitesla for a big superconducting slab. But the aluminum was still superconducting.
Thanks.
I guess we all have our favorite devices. So there's 4 on this slide. Does anyone else want to propose some, you know, for discussion, alternative designs?
I'm kind of curious, Jason, that you mentioned that maybe one of the bullet topic is maybe you can go back to some of this non-abelian states in fractional quantum world, say 5Fs, for example, right? Is there some after all that was the initial system that community started out just looking for non-abelian anyons, but then more like that moved away, but after all that, after we learn all this lesson, is there something that if you just revisit, do we have the new ideas or fresh new directions? What make you think that it's time that maybe we can also revisit?
Well, I mean, my logic is largely based on the recent breakthroughs that have happened in abelian demonstration of abelian statistics, and so it now feels like perhaps the interferometric detection of non-abelian statistics is perhaps not as far off as it seemed even, you know, a year ago or so. You know, also I think 2D materials is a certainly a newcomer, not that newcomer, but, you know, compared to the original gallium arsenide days, and so. It's not just gallium arsenide. We now have lots more platforms along which to pursue that goal. So you know, I think this is not an obsolete direction, and you know, I think there's a non-trivial chance that maybe in the couple-year time scale, the anyon interferometers that have been demonstrated now for the abelian case can be pushed into the non-abelian regime. One has to rely on a certain amount of luck. I don't know how much luck is required. I mean, you need non-abelian phases to really be there, and that's, you know, that was kind of the beauty, at least to me, a lot of the beauty of what happened in this field in the last decade is that we removed serendipity from the equation and made all these nice designer platforms. That has led to its own set of challenges. But if I mean, serendipity, if you can take advantage of it, is a pretty nice thing, and gifts from nature when they appear, we should not take them for granted. And you know, maybe non-abelian fractional quantum Hall states are in that category.
Remember, like a side discussion for this non-abelian or a parallel discussion for non-abelian phases in quantum Hall states in particular was non-abelian phases that emerged from bilayer quantum Hall systems with the possibility of doing some braiding operations between layers. I remember particularly talks by Mason Barkeshley on this. I was wondering, where did that direction go? Is it motivating experiments? Is it reasonable experimentally? Did we make progress towards states like that?
Gil, just to make sure I understand the context, are you thinking about like the Barkeshley ideas for using bilayers to get like parafermionic zero modes via defects?
Yeah.
I think that idea is still around.
Complete gate sets.
Yeah, I mean that's I think very much a beautiful idea. To me, that idea rose to a little bit closer to reality following experimental discovery of fractional Chern insulators in Andrea Young's group. I mean, in that context, it's conceivable that you could actually engineer some kind of lattice, extrinsic lattice defects to, via some set of gates to realize that version of parafermionic defects. I think if we could get a zero field fractional Chern insulator, that's not yet discovered, but that would, I mean, I think really open the floodgates for using that strategy. I don't know about the bilayer idea. Maybe I don't know if Philip or other experimentalists have.
I don't know about that. Yeah. But I think that since you mentioned about the zero field Chern insulator, the again zero field Chern insulator versus just the quantum states, or zero field fractional Chern insulator versus fractional quantum states. Besides there is a magnetic field presence, do we see that kind of really fundamental difference there?
No, it's the same phase of matter.
Yeah.
But I think, I guess in the theme of this slide, doing away with magnetic fields, I think at least most people may agree is a nice thing, maybe not universally, but actually, maybe I can add something there. If you can get a fractional Chern insulator at zero magnetic field, then I think the issue of slapping on a superconductor, modulo the kind of caveats that I gave before, that becomes much less of a dangerous thing to do. You don't have to worry about vortices or any high field physics like that. But a gift from nature of that type has not yet been delivered, as far as I'm aware.
Just a, can I? Oops. Let's see. Can I make a comment?
Of course, yeah.
So just to remind you that in terms of braiding of non-abelian or interference, at least, of non-abelian excitations in quantum Hall states. So Bob Willett has been claiming for years that he's seen it, and the most recent set of experiments from, I guess, 2019 are certainly impressive. I think there are questions about what's really going on there. It is very hard to understand what the actual geometry is in his, or how he achieves the geometry that he claims that he seems to be achieving in terms of a very, very small quantum dot, if you wish, or interferometer area that's much smaller than the lithographic area and has a weird shape. And there are a number of questions about it, and he's not seeing individual, well, he sees even odd type excitations, but he doesn't even odd type alternation, such as you would expect if there was if there were these if there were non-abelian statistics, but he's not really seeing clean jumps from even to odd. It's more a statistical thing where he's Fourier transforming it, and it could be explained by, I think, again, within the general framework of what he's done, you can understand it as an E/4 type excitation, 1/4 charge electron excitation circulating around the interferometer area. And what's happening inside is that you're perhaps you could be adding E over 2 excitations inside, or you could be adding E over 4 excitations that pair up to form E over 2 excitations. They have to kind of always pair up when you add them, so that they're always in the same topological phase, or mostly in the same topological phase. Otherwise, he wouldn't see what he's seeing. And none of that is well understood. And I don't think you could say it's cleanly showing fractional statistics per se, but it's on the way there to showing that the modulo, that we don't understand it completely, that it is showing some effects of an E over 4 quasi-particle, at least, doing interference around a system that changes periodically as you change the number of electrons in it, or charges in it, or magnetic field flux quanta in it. So I don't think one can dismiss it. I think it's very hard experiments, obviously, and there remain questions, as there have been, but he's gone a long way, I think, to cleaning it up from what he was doing 10 years ago. And again, when you talk about we shouldn't rule out the original platform, we also have to take into account what has been done there.
Yeah, well, thank you. I really appreciate that remark. I in hindsight, I regret not mentioning that those experiments from Willett. So, I should say I'm not I don't feel qualified to comment on the extent to which those experiments are clear cut. My impression from experts on that subject is that it remains controversial, and so really I had in mind something of the spirit of these abelian interferometry experiments, which, at least as far as I've been able to glean from hearing discussions and talks about this, I haven't sensed much skepticism about the origin of what's seen there, and so hopefully we can get to that level also in the non-abelian case. So that's kind of what I had in mind. But thanks, Bert, for
well, that would be very nice. It's still a long way, but I should say there is still some skepticism. I've heard some experimentalists challenging, questioning the latest abelian stuff too. So I think there's always some controversy, but okay, there's a big difference.
Gotcha. Yeah, thanks, Bert.
Maybe I wanted to look back to something that Carsten mentioned tomorrow. It's a kind of broader comment, which was, Carsten had basically the question that we all ask is, why has it been 10 years and we haven't had like very convincing signatures of Majorana, if you look critically at it. And I think one of the problems is, which Carsten also mentioned yesterday, is that there are many experiments have been done and they were unsuccessful. And basically, if I look at it, and I've been working in this field partially for the past 5 years, I can't even name the experiments that have been done and why they were unsuccessful, for example. So maybe a good thing to do would be to be more open about sharing not successful experiments, and maybe as journal editors or so, and many of you are journal editors in some capacity, to invite issues on well-designed and well-thought-out experiments that were not successful, and maybe try to figure out why they weren't. Because I feel if a field is stuck or not moving fast, as Majorana research is at the moment, it's very important to understand what are the problems. And personally, I always found it more helpful to talk with experimentalists about why the experiments don't work and what are the problems than to actually look at the kind of finished product at the end. So I think maybe that would be something very useful. And, yeah, maybe one can either open some kind of forum, either in terms of a journal or as part of some journal as a special issue, to invite such submissions.
Yeah, I've heard, I don't know if this is exactly what you're suggesting, but are you proposing like a journal of null results, which I've heard?
Yeah, I mean, in other sciences, this is a broader problem in science that basically positive results are kind of overstretched and negative results are not communicated, right?
Well, I have maybe a suggestion. Maybe we can collectively write the editors of Nature to ask them to start a Nature null results subjournal.
Yeah, I mean, I think there's different approaches to this, right? So one is where basically a priori people submit a study design or something like that, which is done in the social sciences or medicine or so, where people submit a priori what they want to do, what are the goals, what are the expected outcomes, and then they get to publish something no matter whether it was successful or not, right? I think also now after experiments have already been done, it would just be useful to have a resource where, I mean, one can judge good science independent of whether the expected outcome was reached or not, right? You can judge as a referee whether an experiment was well thought out and well performed on a technical level without knowing or judging that the experiment gave you the result that you wanted, right? And arguably that's a better way to judge how an experimental research is done, right? I think that would be very useful to collect these results, because basically, even for me working in this field, I don't have a good idea why specific experiments didn't work, or I don't even know how much or how hard they have been tried. Right? And this kind of information would be very useful, because even now, if I look at the archive and I have some idea of what are good ingredients in a Majorana design and what are bad ingredients in a Majorana design, if I look at the archive for theorists in particular, more than half of the papers contain some kind of ingredients in their device designs or so, which I already know are not very realistic, maybe, right? And I think it's really a problem in communication between experimentalists and theorists. And much of this knowledge of what isn't easy to do experimentally is kind of translated by folklore, by discussions in conferences, but not like really documented. So I think that would be very useful to have some kind of better documentation of this.
Well, we could have a conference about it. It's not necessarily null results, it's just things that worked out differently than you expected.
Yeah, I mean, I'm happy to help. I think it would be good to have some kind of more prominent people than myself, because if I go to Nature and tell them I want to publish null results, then they're going to tell me no. But if someone who's kind of more of an authority can try to get some leverage there.
Well, I don't know if one needs to go to the journals necessarily, but
no. But I mean,
you just have a meeting and discuss things like we're doing now.
By the
Yeah,
way,
that's
you
what
mentioned
conferences used to be for. You know, do you remember those times where we met and discussed like experimental progress over beer without committing to the results?
Right.
So hopefully this will come back.
Let me mention that you are mentioning Nature, but it also happens with science, and we have a science editor in the audience. I'm just saying.
Oh, we do?
Oh yeah, sure. I can do it. Okay, let's see if you thanks. Bye.
I think as an experimentalist, especially working in the mesoscopic type of the devices, sometimes you know that the failed success is sometimes it's a little bit hard to distinguish, right? I think that this was the configuration is different. Every device, even if you just make it the same way, they have the different natures. So sometimes, often it's not a clear cut. Why what do you call this is the work device and what is called a not work device? Often then you have to present some of the statistics, device statistics, right? How many devices you see the similar things. So often that it's not a clear cut that just look back at my own group's work, right? When we just kind of make the report, of course you just kind of tend to just show the best set of the data, but also you just kind of mention about the statistics, if it is something not working out, how do you just exclude those kind of things that it's a little bit complicated whether I can have the bunch of the paper I can just submit into the journal of the no result type of things. In fact, I feel like that it is better that within a result or a paper described the all the statistics a little bit more carefully and documented it. In fact, many of the work, the experimental work, often that is documented. It was mentioned usually in the supplementary material, supporting information, those kind of category. But experimentalists also do supply that those kind of information. Often that's not emphasized, indeed, right? That might be the complaint that the theorists can make.
Oh yeah, I mean, I don't want to take the high ground on this, right? This is completely, but I think it would be very useful to have this information, because I know I've been in Copenhagen, spent there half a year, and I discussed with Charlie Marcus' group a lot. I think that would apply to any group where you have close contact with. I found the discussion about why stuff doesn't work basically more useful than any published paper. So yeah, I think it would be very useful to encourage this more. Also as a reviewer, I guess. I mean, if you see a paper where they have 2 or 3 devices at work and they don't mention, let's say, even in the supplement, any devices that don't work, or they don't document the devices that don't work, I think that's just not a good paper, because it's kind of unrealistic to expect that you only make 3 devices and everything works, right?
So we're running past a lot of time to the conference, and this has been a really lovely discussion, and it's been great to see so many of you, as could fit on my screen. But I suggest we wrap up the discussion. So Jason, would you like to say any concluding remarks for the discussion of the session?
Maybe just thank you to the organizers and to all the people that participated in the discussion, and the people that gave great talks. It was a nice break from ordinary my ordinary day to hear some of these developments, and so thanks again to the organizers.
Yeah, as the least working organizer, I would like to thank my co-organizers, particularly Tommy and Kartik and Yuval, and all the speakers and all the discussion leaders, all the participants, and particularly the participants who are in Asia right now, who are dying to go to bed. Thank you for sticking with us. So hope to see you all in person before too long. And Tommy and Kartik, maybe you would like to take the speaker and take the microphone and conclude.
Just want to say thank you to everyone, the speakers, and especially the discussion leaders. I think this is a non-conventional task that we asked you to do, and everybody did it so well. So thank you all.
Yeah, I just the same thing. Absolutely, it's been a pleasure to hear all these talks and interact with you all. So it's been great. Thank you very much, everyone. Have a good rest of the day.
And thanks to the KITP staff, to Mark and company who facilitated this and made it possible in providing us with a venue. So thanks. So with that, I think we can conclude the conference. Thank you all. Really good to see you. Keep safe.
Thank you. Bye-bye.
Bye-bye.